These are the solutions for the Module 6 Problems for Students Part 2. Again, this is a solubility equilibrium problem. We're given an equation where we have magnesium fluoride dissolving to magnesium ion plus 2 fluoride ions. The problem statement says in a saturated solution of MgF2 at 18 degrees C, the concentration of magnesium is 1.2 times 10 to the minus third molar. The equilibrium is represented by the equation above. So we're tasked with four things. We need to write the expression for KSP, calculate its value at 18 degrees. We need to calculate the equilibrium concentration of magnesium ion in 1 liter of saturated MgF2 at 18 degrees, to which 0.1 mole of solid KF has been added. The KF dissolves completely. Assume the volume change is negligible. Part C, predict whether a precipitate of magnesium fluoride will form when 100 milliliters of a 3 times 10 to the minus third molar magnesium nitrate solution is mixed with 200 milliliters of a 2 times 10 to the minus third molar sodium fluoride solution at 18 degrees. Calculations to support your prediction must be shown. In Part D, at 27 degrees C, the concentration of magnesium in a magnesium ion in a saturated solution of magnesium fluoride is 1.17 times 10 to the minus third. Is this an endothermic or an exothermic process? Give an explanation to support your answer. Like last time, this is a pretty daunting problem, but like last time, it's doable. So let's start. All right, so we're going to write the expression for the solubility product constant, KSP, calculate its value. We write the reaction. It's just a copy and paste from the original reaction that we're given. This time we know the molar concentration of magnesium ion, and because of stoichiometry, we can get the fluoride ion concentration. It's twice the magnesium ion concentration, and this is going to allow us to compute KSP pretty straightforward. We write our reaction equation, our KSP equation. We plug in the value of Mg2 plus. We multiply that value by 2 to get the value of F minus, and we square it because that's what you do for the KSP expression when the stoichiometric coefficient is 2. So once we do all that math, we get KSP is 7.09 times 10 to the minus ninth. That's our answer for Part A. Pretty straightforward. Part B, calculate the equilibrium concentration of magnesium ion in a liter of saturated magnesium fluoride solution at 18 degrees C, to which 0.1 mole of solid KF has been added, and this dissolves completely. Assume the volume change is negligible. All right, now we have what's called a common ion problem. Common ion here is fluoride. We already had magnesium fluoride, and we have some other, we have potassium fluoride. Potassium fluoride is pretty soluble. Magnesium fluoride is not. So the fluoride that is part of the potassium fluoride is going to contribute to the overall equilibrium problem. It's going to shift the equilibrium to the left to consume the added fluoride ion. And this is going to reduce the amount of Mg2 plus in solution, but we don't know by how much. This is one of those problems where an icebox is pretty useful, okay? So let's set this up. We've got our reaction at the top, but now we have an initial concentration. Our initial concentration of magnesium before we start, before the KF is added, is 1.21 times 10 to the minus third. For the fluoride, it's twice that, 2.42 times 10 to the minus third, but we've also added 0.1 mole. So we write 0.1 plus 2.42 times 10 to the minus third. What's the change? Well, magnesium is going to change by x. We don't know how much. But the fluoride, it changes by minus 2x. And the reason we put minus here instead of plus is because the equilibrium is going to be shifted back to the left. If I add a common ion, Le Chatelier's principle says that the reaction shifts to alleviate the stress that's put on it. I've stressed the system because I put another ion in there that I already have. So now that equilibrium shifts back to the left, which is going to consume some of the magnesium. So we write that as a negative quantity. At equilibrium, we just sum those two values, initial plus change. So I get 1.21 times 10 to the minus third minus x, and 0.1 plus 2.42 times 10 to the minus third minus 2x. Well, that's going to be some messy algebra. We can write our equilibrium expression though, so let's do that. We get 7.09 times 10 to the minus ninth is the product of the magnesium equilibrium expression and the fluoride equilibrium expression. That is pretty ugly. We could solve this by brute force, but unless you are just a glutton for punishment in algebra, this is going to take a while and it's going to be hard. Can we simplify it? Yeah, maybe we can. Let's assume that x is pretty small such that the second term is really 0.1. If I look at 2.42 times 10 to the minus third, that's 0.00242. And if I assume that x is pretty small, then that entire term is going to be about 0.1. So that allows me to make the simplifying assumption, and now I can solve for x. All right, otherwise I'd have a 4x squared, and it would just be kind of a mess. We think we can get away with that because if x is small, then x squared is going to be even smaller. So now if I solve for x, I get x is 0.001200929. We're going to abbreviate that or round that to 1.21 times 10 to the minus third. Okay? So at equilibrium then, the magnesium concentration will be 1.21 times 10 to the minus third minus our value of x, which we write in its entirety, otherwise we would get 0. As it is, we get a pretty small number. Now we don't write that on our piece of paper, but we keep the number in our calculator and let our calculator do our computing for us, and we get a really small number, 7.09 times 10 to the minus 7th molar. Okay, so that's our answer to part B. Part C, predict whether a precipitate of magnesium fluoride will form when I add a certain quantity of magnesium nitrate to sodium fluoride. Support with a calculation. Okay, now first we have to determine, is anything even going to precipitate out as a solid? So if I mix magnesium fluoride with sodium fluoride, sorry, that should read magnesium nitrate is mixed with sodium fluoride, we have a double displacement reaction. So our two possibilities are either magnesium fluoride or sodium nitrate. And since all nitrates are soluble, and since we already know that magnesium fluoride isn't soluble, it's a pretty easy choice. So whether or not a precipitant forms depends on the solubility product constant. Now, if we do this calculation and we get a number less than the KSP for that product, then our solubility limit hasn't been reached and we don't get a precipitant, even though we're calculating a thing that might precipitate, its concentration isn't high enough to exceed that solubility limit, so there's no precipitation. If, on the other hand, it's greater than the KSP, then we do get a precipitant. And so now we can calculate the concentrations. We have 100 mils of one solution, 200 mils of another, so I get 300 milliliters total. Now we're going to do a trial KSP calculation to see if we exceed the known KSP value or not. So KSP is magnesium concentration times the fluoride concentration squared. We put the quantities which we know in there, 1 times 10 to the minus third and 1.33 times 10 to the minus third squared, and we get 1.77 times 10 to the minus ninth. Oops. So I've got my little sequence out of order. I calculated my magnesium ion concentration to be 1 times 10 to the minus third. My fluoride concentration was 1.33 times 10 to the minus third, and that's where those numbers come from. Since 1.77 times 10 to the minus ninth is less than 7.09 times 10 to the minus ninth, which is our known published value of KSP, we don't get a precipitant. All right, part D, we want to know, is this endothermic or exothermic? So the only thing that really changed in these parts is the temperature. So I've got 18 degrees versus 27 degrees. So here, this is just a recap of the stated solubility. So I can see as the temperature goes up, the solubility goes down. So if I were to graph that, I would get a line with a negative slope. And as we've discussed in class, it's either endothermic or exothermic. So if I increase the temperature, I add more heat. Le Chatelier's principle says the equilibrium will shift to relieve the stress, which would be to the right. But that's not what we see. We see the opposite of that. So that means that this is an exothermic process. That concludes these sets of questions. If you have any additional questions, contact me in class.